Hi guys, Stat Lessons here, got another 20 for you. This one's on AI search endpoint tiers, retrieval ranking metrics, and MLflow Model Lifecycle. Quick countdown of 10 seconds per question. Then the answer. Pause if you need more time on any of them. Now, question 1. Small wording, big difference. A generative AI engineer at Vertex Commerce is building a product search system for a catalog containing 1.8 billion product vectors at 768 dimensions. The current standard AI search endpoint cannot keep the index synchronized as the catalog receives continuous updates. Which action should the engineer take to accommodate this workload? Select 1. Review the answer choices on screen. The correct answer is option A. Partitioning across 4 standard endpoints doesn't resolve. Storage-optimized AI search endpoints are specifically designed for datasets exceeding 1 billion vectors and deliver 10-20x faster indexing throughput compared to standard endpoints, which is essential for keeping a 1.8 billion vector catalog synchronized under continuous updates. The accepted trade-off is approximately 250 milliseconds additional query latency. Standard AI search endpoints support roughly 320 million vectors at 768 dimensions, so distributing the catalog across 4 standard endpoints does not resolve the fundamental capacity and indexing speed limitation of the standard tier. Reducing embedding dimensions degrades semantic search quality and does not address the indexing throughput bottleneck. Change data feed is a prerequisite for delta sync indexes of any endpoint type and does not raise the throughput ceiling of a standard endpoint. Let us keep moving. Question 2. The wording is the clue. A generative AI engineer is evaluating the retrieval component of a case law search tool built for litigation attorneys. The attorneys report that when multiple relevant precedents exist, the order in which cases appear at the top of results strongly influences how they structure legal arguments. The engineer wants a metric that directly captures whether the most critical cases are ranked highest, not merely whether they appear somewhere in the results set. Which retrieval metric best addresses this requirement? Select 1. Review the answer choices on screen. The correct answer is option D. Ranked highest, not merely present, that phrase decides. NDCG, normalized discounted cumulative gain, at K, is the correct metric when ranking order within the result set is the primary concern. It assigns higher credit to relevant documents placed at earlier positions and penalizes systems that bury the most important results further down the ranked list, directly measuring the attorney's concern that case ordering affects argument quality. Recall at K captures whether relevant documents are present anywhere within the top case set, but assigns no credit based on whether a critical case appears first or last within that set. Precision at K measures the density of relevant results within the top case set, but also ignores positional ordering entirely. F1 at K is a harmonic mean of precision and recall and inherits the same positional blindness from both of the metrics it combines. Let's spend a minute on this one. Retrieval metrics can look similar until you focus on what they actually measure. Imagine 2 search systems both return the same 5 relevant cases. System A buries your strongest precedent at position 9. System B puts it first. Recall at K scores them the same. It checks whether relevant cases appear at all, not where they land. Precision at K has the same blindness. It counts relevant hits but ignores order. F1 at K combines both, so it inherits both problems. NDCG, normalized discounted cumulative gain, works differently. It applies a log discount. Position 1 earns full credit, and credit shrinks as you go deeper. A system that ranks your best case first scores higher. When attorneys argue from the top down, NDCG at K is the only metric that rewards that. Let us keep moving. Question 3. Use elimination aggressively. A generative AI engineer at Thornton Retail is building a product recommendation assistant using feature serving. The assistant needs to retrieve a customer's pre-materialized purchase history from a registered feature table and compute a real-time discount eligibility score derived from their current loyalty tier at serving time. Which two feature spec components should the engineer use? Select 2. Review the answer choices on screen. The correct answers are option A and option C. 3 of these 5 options simply don't exist. Feature lookup retrieves pre-materialized columns from a registered Unity catalog feature table by matching on a specified lookup key, making it the correct component for pulling stored purchase history records. Feature function defines a Python function that is applied at serving time to compute on-demand derived values, such as discount eligibility from loyalty tier data, enabling real-time transformations without requiring those values to be pre-materialized. Feature pipeline, feature stream, and feature cache are not valid components of the Databricks Feature Spec API and do not exist in the feature serving framework. Time for another one. Question 4. Translate the story into requirements. A generative AI engineer at Claridge Biotech is building a RAG assistant for medical researchers. The system must answer questions using 2 data sources: unstructured research papers stored as PDFs and real-time clinical trial enrollment counts from a database updated every 15 minutes. Which 2 approaches should the engineer use to handle these data sources? Select 2. Review the answer choices on screen. The correct answers are option A and option C. Each data source type demands a different retrieval strategy. Research papers are unstructured data that benefit from chunking and embedding into a vector index, allowing the RAG system to retrieve relevant passages based on semantic meaning. Feature serving is designed for real-time structured data. It exposes pre-computed and continuously updated values through a low-latency, auto-scaling endpoint, making it ideal for enrollment counts that change every 15 minutes. Converting structured numerical data to Markdown and embedding it loses precision and creates a poor retrieval target for specific numerical queries. Applying semantic chunking to tabular data does not preserve relational structure and is inappropriate for structured enrollment statistics. Storing papers as raw files and passing paths to the LLM bypasses retrieval entirely and does not ground the model in relevant document content. Time for another one. Question 5. Watch for the hidden requirement. A generative AI engineer at Northwind Logistics has been running a pay-per-token foundation model API endpoint for an internal shipment routing assistant. As usage grows, the team observes inconsistent response latency during peak hours that violates their SLA. The engineer needs to guarantee a minimum token throughput level while still allowing the endpoint to scale upward during traffic spikes. Which configuration approach should they implement? Select 1. Review the answer choices on screen. The correct answer is option A. Pay per token has no floor. Provisioned throughput does. Provisioned throughput endpoints require setting min_provisioned_throughput and max_provisioned_throughput, which define the lower and upper bounds of the guaranteed tokens per second scaling range. This ensures the endpoint delivers predictable performance under peak traffic by reserving a minimum capacity floor, resolving the latency variance that pay-per-token endpoints cannot guarantee. The num_replicas and max_concurrent_requests parameters apply to custom model serving configurations, not to foundation model API provisioned throughput endpoints, which use a token-based scaling model rather than replica counts. The sampling underscore fraction is an inference table parameter controlling what fraction of endpoint requests are logged for monitoring purposes and has no effect on traffic routing or latency. The RRF underscore param is a reciprocal rank fusion parameter used in AI search hybrid query configuration and is entirely unrelated to model serving throughput management. First 5 questions cover storage-optimized endpoint capacity, select 2 traps with non-existent feature spec components, and provisioned throughput's guaranteed minimum floor, pay per token cannot promise latency SLAs. Ready. Question 6. Parse the sentence before the options. A generative AI engineer at Tailspin Analytics has fine-tuned a document summarization model for the legal team and is ready to register it to production. The workspace runs MLflow. The default registry URI is Databricks UC, and the team's models must live in a Unity catalog named prod_catalog under a schema named legal_models. Which value should be passed as the name argument to MLflow.register_model to satisfy Unity catalog governance requirements? Select one. Review the answer choices on screen. The correct answer is option B. Unity Catalog enforces 3-level delimited namespace always. Unity Catalog enforces a 3-level delimited namespace for every managed object, including registered models. The required format is catalog.schema.model_name, so prod_catalog.legal_models.document_summarizer is the correct argument for MLflow.register_model. Providing only document_summarizer without the catalog and schema qualifiers either resolves to the legacy workspace level registry or raises an error because MLflow 3's default registry URI is Databricks UC, which requires fully qualified 3-level names. // are path separators in file systems and object storage, but are not valid namespace separators in Unity Catalog syntax. Parsing them causes the registration call to fail with a parse error. Colons are equally invalid as namespace delimiters for Unity Catalog objects and produce the same failure. Ready. Question 7. The answer hinges on one qualifier. A generative AI engineer at Meridian Media is building a content moderation system that must analyze both thumbnail images and short promotional video clips to detect policy violations. The system should process both modalities in a single model call without any additional pre-processing pipeline. Which foundation model API model should they select? Select one. Review the answer choices on screen. The correct answer is option B. Claude Sonnet 4 handles images but not video natively. Gemini 2.5 Flash natively supports all 4 input modalities: text, image, video, and audio, making it the only model that can process both thumbnail images and video clips in a single model call without any additional pre-processing. This native video support is the decisive differentiator that allows a single model call to analyze both content types for policy violations. Claude Sonnet 4 supports text and image inputs within the Foundation Model API, but does not support video as an input modality, making it incapable of natively ingesting video clips for policy analysis. Llama 4 Maverick similarly supports text and image inputs only, and cannot process video content without a separate frame extraction step that reroutes the workload outside the model's native capabilities. BGE Large is an embedding model that produces vector representations for retrieval and similarity search. It cannot interpret visual or video content, cannot detect policy violations, and cannot generate text output of any kind. Ready. Question 8. Look for the limiting phrase. A generative AI engineer at Coalfield Genomics needs to index a dataset of 1.5 billion high-dimensional embeddings. The team can tolerate a modest increase in query latency, but needs 10-20x faster indexing throughput than the standard configuration provides. Which endpoint configuration should they use? Select one. Review the answer choices on screen. The correct answer is option A. Over 1 billion vectors always means storage-optimized. Storage-optimized AI search endpoints are designed specifically for datasets exceeding 1 billion vectors and deliver 10 to 20 times faster indexing throughput compared to standard endpoints. The trade-off is an approximately 250 millisecond increase in query latency, which the team has explicitly accepted. Standard endpoints are designed for approximately 320 million vectors at 768 dimensions and cannot efficiently handle a 1.5 billion vector data set. A direct access index requires the caller to supply and manage pre-computed embeddings externally, adding unnecessary operational burden when Databricks managed embeddings through a Delta Sync index fully satisfy the requirements. Combining a direct access index with a storage-optimized endpoint adds the same external embedding management overhead without any benefit over the managed approach. Keep your focus here. Question 9. Pay attention to what is really asked. A generative AI engineer at Northwind Publishing is evaluating the retrieval quality of a RAG system built over a catalog of 50,000 academic articles. For each test query, the evaluation set assigns relevant scores of 0, 1, 2, or 3 to candidate documents. The engineer needs a metric that captures both the graded relevance intensity of retrieved documents and the importance of returning the most relevant results at the top of the ranked list. Which metric should the engineer use? Select one. Review the answer choices on screen. The correct answer is option D. The 0 to 3 scoring scale is the giveaway here. DCG at 10, discounted cumulative gain at rank 10, is purpose-built for this scenario. It uses the 0 to 3 graded relevance scores to measure relevance intensity, distinguishing between a highly relevant document, score 3, and a marginally relevant one, score 1, and applies a positional discount so that highly relevant documents appearing first contribute more to the final score than those ranked lower. Recall at K measures completeness by counting how many known relevant documents were retrieved, but it treats all relevant documents as equally important and ignores ranking position. Precision at K measures the proportion of retrieved documents that are relevant, but similarly ignores graded relevance levels and ranking order. F1 at K combines precision and recall into a single score, but still treats relevance as binary, and does not account for the position of results in the ranked list. Let's slow down here. The DCG metric hides a trap that trips up most people. Imagine you searched for machine learning and the best paper ever written shows up at rank 10. Should that count the same as finding it at rank 1? DCG, discounted cumulative gain, says no. It multiplies each document's score by a weight that shrinks the further down it appears. A score 3 document at rank 1 contributes 7.0 points. At rank 2, it gives 4.4 points. By rank 5, it's down to 2.7. At rank 10, just 2.0. Notice how the bars shrink. That's the discount. Precision, recall, and F1 don't do this. They treat every position the same. That's the trap. The question gives you 0 to 3 graded scores and cares about position. DCG is the only choice that handles both. Keep your focus here. Question 10. Avoid the familiar but wrong answer. A generative AI engineer is using Databricks AI search with hybrid search enabled. After initial testing, the engineer notices that documents with high repetition of domain-specific keywords are consistently outranking more concise, accurate answers. The engineer wants to tune BM25 to dampen the advantage of repeated keywords while leaving document length normalization unchanged. Which configuration change should the engineer make? Select 1. Review the answer choices on screen. The correct answer is option D. K1 controls saturation. B controls length. Don't confuse them. The K1 parameter in BM25 controls term frequency saturation, the rate at which additional occurrences of a term stop, meaningfully increasing a document's score. Lowering K1 causes saturation to kick in sooner, so the 50th occurrence of a keyword contributes far less marginal gain than it would at a higher K1 value. This directly resolves the problem of keyword-dense documents drowning out more focused answers. The B parameter governs document length normalization rather than term frequency behavior. Increasing B would penalize longer documents broadly, but would not specifically dampen the influence of keyword repetition, and the engineer explicitly wants to leave length normalization unchanged. Decreasing B reduces length normalization entirely, which would amplify the existing advantage that long, keyword-heavy documents already enjoy. Increasing K1 raises the saturation ceiling, making each additional keyword occurrence more influential, which is the opposite of what the engineer needs. This one's a BM25 tuning question. Let's map which dial to turn and why. Imagine a document that just repeats the word fever 50 times. In BM25, the doc could beat a perfect, concise answer. BM25 has two dials you care about. K1 controls how much each extra repetition of a keyword boosts the score. Think, how greedy is repetition? B controls length normalization. How much long docs get penalized? The problem here is repetition, not length, so touch K1, not B. Decrease K1 and that 50th fever adds almost nothing to the score. The trap is grabbing for B. The question says leave length normalization alone. That's why D wins. 6 through 10. Unity catalog. Notation is non-negotiable. Gemini 2.5 Flash is the only native video model available, and lowering BM25 K1 dampens keyword repetition advantage, not the B parameter. Alright, question 11. Underline the key phrase mentally. A generative AI engineer at Kirkwood Data is migrating a legacy document search system to Databricks AI Search. Their existing Delta source table uses a column named _i.d as the primary document identifier. When they attempt to create a Delta sync index on this table, the operation fails with an error. What is the most likely cause of the failure? Select 1. Review the answer choices on screen. The correct answer is option D. CDF is often the suspect. Here it isn't. The column name _i.d is a reserved identifier in Databricks AI Search and cannot exist in any source Delta table used to create an index. The engineer must rename this column before attempting index creation. A missing change data feed would prevent the index from synchronizing incrementally, but it produces a different error about CDF not being enabled rather than an immediate column naming conflict. Unity catalog registration is a prerequisite for the workspace to support AI search at all, but this would surface as an authorization or workspace configuration error, not as a column naming failure. The HNSW algorithm is the underlying approximate nearest neighbor mechanism for all AI search indexes, and does not impose any restrictions on column names or data types. Keep your focus here. Question 12. Read it carefully. A generative AI engineer at Litware Insurance is deploying a customer-facing claims assistant that processes requests containing social security numbers, phone numbers, and email addresses. Regulatory requirements mandate that this personally identifiable data must not be passed to the underlying LLM or captured in any request log. Which AI gateway guardrail feature should the engineer configure? Select 1. Review the answer choices on screen. The correct answer is option C. Safety filters block harmful content, not personal data. PII detection and redaction scans incoming requests and outgoing responses for personally identifiable information, including social security numbers, phone numbers, and email addresses, and replaces them with placeholder tokens before the data reaches the model or any logging system. This directly satisfies the regulatory requirement to prevent PII from being transmitted to the LLM or stored in logs. Safety filtering blocks harmful content categories such as hate speech, insults, sexual content, and violence, which is a content moderation concern unrelated to protecting personally identifiable data. Rate limiting controls how many requests a user or group can send per unit of time and governs throughput without providing any data privacy protection. Traffic splitting distributes requests across multiple model endpoints for gradual rollout, and has no mechanism for detecting or masking sensitive personal information. Okay, question 13. The wrong answers are close. A generative AI engineer configured an inference table to capture all production requests for a deployed summarization endpoint. 6 weeks after deployment, the team discovers that no new requests have appeared in the inference table for 2 days, even though the endpoint is actively serving traffic successfully. What is the most likely cause? Select 1. Review the answer choices on screen. The correct answer is option A. Sampling fraction 0.5 reduces records. A schema change stops all. Databricks inference tables stop logging when the schema of the inference table is modified. Adding, removing, or renaming columns breaks the internal logging pipeline and Databricks ceases writing new records to the table. This is a documented constraint. Downstream analytics pipelines built on inference table data must read the table as is without altering its schema. The 128 concurrent request limit is a throughput constraint that causes request failures or queuing when exceeded. It has no effect on inference table logging. A sampling fraction of 0.5 reduces capture volume to roughly half of all requests, but does not halt logging entirely. Any such change would still produce records for the captured fraction of traffic. Status code 200 responses represent successful requests and are always written to the inference table when logging is active. Only certain error codes such as 401, 403, 429, and 500 may be omitted. Okay. Question 14. A generative AI engineer is building a search application for a law firm that must surface documents matching both exact statutory citations and broader semantic intent. The engineer wants to configure a single Databricks AI search index to handle both retrieval modes without maintaining separate indexes. What type of index and result combination approach should they configure? Select 1. Review the answer choices on screen. The correct answer is option C. 1 index, 1 query. Hybrid search fuses both modes. Databricks AI Search supports hybrid search by enabling both BM25 keyword retrieval and approximate nearest neighbor vector search within a single delta sync index. The scores from both retrieval modes are fused using reciprocal rank fusion with a default RRF_param of 60. Producing a unified ranked list that captures both exact term matches and semantic similarity in one query. Configuring BM25 only with post-processing re-ranking is a two-stage pipeline that adds latency and misses the native fusion that hybrid search provides within the index itself. A direct access index requires the caller to manage embeddings and does not natively support hybrid search fusion. Using two separate indexes merged in the application layer duplicates infrastructure and forces the application to handle result merging, which is precisely the complexity that native hybrid search eliminates. Okay. Question 15. Start with what the user needs. A machine learning platform team at Contesso manages a text summarization model with multiple registered versions in MLflow Model Registry backed by Unity Catalog. The production inference pipeline currently hardcodes a specific model version number. The team wants to update the pipeline so that promoting a new model to production no longer requires a code change or redeployment of the inference pipeline. What is the recommended approach? Select one. Review the answer choices on screen. The correct answer is option C. Secrets and schema paths add friction. Aliases eliminated. MLflow Model Registry in Unity Catalog supports named aliases such as champion that can be reassigned to any registered version. Loading the model by alias means the inference code never needs to change. When a new version is approved, the platform team updates the alias mapping, and the pipeline automatically loads the new version on its next run. Logging the version number to an experiment run parameter introduces a fragile dependency where the pipeline must query MLflow for its own configuration, creating an indirect coupling that is easy to break. Maintaining a separate production schema requires updating the registration path on every promotion and adds operational overhead without versioning benefits. Databricks secrets are designed for credentials and tokens, not for model version bookkeeping, and this approach still requires an explicit manual update to the secret each time a version is promoted. 11 through 15 surfaced three distinct failure modes. A reserved column name breaks index creation, a schema change silently kills inference table logging, and hard-coded version numbers break without an alias. Here we go. Question 16. Every phrase counts. A generative AI engineer at Clearwater AI is evaluating the response quality of a news summarization assistant. The team wants an evaluation approach where the judge produces explicit step-by-step reasoning before arriving at a quality score. So engineers can inspect why a particular score was assigned and identify systematic failure modes. Which evaluation methodology best meets this requirement? Select one. Review the answer choices on screen. The correct answer is option D. Step-by-step reasoning before scoring names exactly one methodology. GEvil with chain of thought prompting instructs the LLM judge to reason through specified evaluation criteria step by step before committing to a final score. This makes the evaluation process transparent and interpretable. Engineers can read the judge's reasoning chain to understand exactly which aspect of a summary caused a lower score and detect systematic failure patterns across many examples. Recall that K measures retrieval completeness against a set of known relevant documents and cannot assess whether a generated summary is coherent, fluent, or accurate. Pairwise comparison reveals which of two outputs is better, but produces a relative preference verdict, rather than an absolute score with visible reasoning, limiting its utility for diagnosing specific failure modes in individual responses. The faithfulness scorer determines whether a summary introduces content not grounded in the retrieved context, which is valuable for hallucination detection, but does not provide the step-by-step interpretable reasoning the team needs. Next up, question 17. Translate the story into requirements. A generative AI engineer at Lakewood Publishing is building a RAG knowledge base over a corpus of long academic research papers. Users need highly targeted retrieval to locate specific facts, but the LLM requires substantial surrounding context to synthesize accurate answers. Which chunking strategy best satisfies both requirements simultaneously? Select one. Review the answer choices on screen. The correct answer is option A. Small chunks retrieve precisely. Parent chunks give the LLM context. Parent-child retrieval directly addresses the tension between retrieval precision and context richness. Small 512 token chunks are indexed and searched, ensuring the retrieval step finds exactly the relevant passage without noise from surrounding content. When a chunk is selected, the system returns its larger 2048 token parent segment to the LLM, providing the surrounding context needed for coherent synthesis. Fixed size 1024 token chunking uses the same unit for both retrieval and context, failing to optimize either dimension. The chunks are too large for precise retrieval and may still omit necessary surrounding context for complex research papers. Semantic chunking produces coherent topic-aligned chunks, but does not inherently provide a separate large context delivery mechanism. The retrieved chunk is what the LLM receives, which may lack sufficient surrounding detail. Recursive splitting with 256 token chunks and 10% overlap maximizes retrieval precision, but gives the LLM very short, context-poor passages that are insufficient for synthesizing nuanced research findings. Next up, question 18. Do not stop at the first match. A generative AI engineer at Northwind Analytics is tracking LLM fine-tuning experiments in MLflow. Each experiment uses a fixed number of training epochs and a fixed weight decay value determined before training begins, records per-step training loss as the run progresses, and includes a label identifying which prompt template variant was used for instruction formatting. The engineer needs to compare runs by hyperparameter values using MLflow's filtering and sorting UI, view training loss as a time series chart in the experiment dashboard, and store the prompt template label as searchable freeform metadata. Which combination of API calls correctly satisfies all three requirements? Select one. Review the answer choices on screen. The correct answer is option A. Static before run equals param, varies during run equals metric. MLflow provides distinct constructs for different kinds of run metadata. Parameters capture static, pre-run configuration values such as training epochs and weight decay. These are recorded with llflow.log_param, support numeric filtering and sorting across runs in the experiment view, and cannot be overwritten once written because they represent immutable inputs to a run. Metrics are numeric values that can change during a run and accept an optional step index, so per-step training loss maps naturally to llflow.log_metric with a step argument, producing the time series training curve visible in the experiment dashboard. Tags are free-form string key-value pairs intended for contextual annotations such as prompt template variant names. MLflow.set_tag stores these as searchable metadata without imposing a numeric type constraint. Recording training epochs and weight decay with MLflow.set_tag converts typed numeric values into untyped strings, preventing numeric comparison and sorting across runs. Calling MLflow.log_param for per-step training loss treats a time-varying signal as a static preset and discards all step information, making training curve visualization impossible. Using MLflow.log_artifact for pre-run configuration values stores them as opaque file blobs that cannot be queried or filtered in the experiment view, eliminating the ability to sort runs by hyperparameter values. Let's slow down here. The MLflow API question is all about matching the right tool to the right data type. Imagine you're training an LLM and want to compare 20 runs side by side. MLflow gives you 3 different buckets, and picking the wrong one breaks the UI. Parameters, like epochs or weight decay, are set before training starts. Use log_param. They're immutable and sortable by number. Metrics, like per-step training loss, change every step. Use log_metric with a step index. That's what draws the time series chart. Tags are free-form string labels, like your prompt template name. Use set_tag. The trap: if you use set_tag for epochs, MLflow stores it as a string. You lose numeric sorting. Wrong type, wrong tool, broken experiment view. Now, question 19. Reason from the scenario. A generative AI engineer at Bellrise Analytics proposes the following sequence for building and deploying a new RAG application. 1. Ingest documents. 2. Index documents in vector search. 3. Evaluate the end-to-end system. 4. Retrieve relevant documents per user query. 5. Generate responses with the LLM. 6. Deploy using model serving. A senior engineer rejects this sequence. What is the specific error in the proposed ordering? Select one. Review the answer choices on screen. The correct answer is option A. You cannot evaluate outputs that don't exist yet. Evaluation depends on the existence of complete system outputs, meaning the entire retrieve then generate loop must execute before any evaluation can take place. Positioning evaluation before retrieval and generation means there are no responses to score for faithfulness, relevance, or groundedness, making the evaluation step meaningless. The correct sequence places evaluation after generation and before deployment. Ingestion preceding indexing is the correct order in the proposed sequence, not an error. Documents must exist before they can be chunked, embedded, and saved to an index. Deployment never precedes evaluation in a standard release workflow. Deploying an unevaluated system would expose production users to a pipeline of unknown quality. The proposed sequence is not valid because placing evaluation before retrieval and generation is a fundamental ordering violation. Let's slow down here. The order of these steps is the whole point of this question. Imagine you're a food critic. You can't review a restaurant that hasn't cooked the meal yet. The proposed sequence puts evaluation at step 3, but at that point, the pipeline hasn't run, no chunks retrieved, no responses written, nothing to score. Evaluation checks whether your answers are grounded in the retrieved context. It needs actual outputs to work with. Here's the right flow. Ingest, index, then let the pipeline run, retrieve chunks, generate responses. Now you have real outputs, say 500 question-answer pairs, to evaluate. Score them for faithfulness and relevance. Only then deploy. Evaluation is downstream of generation, not upstream. Grading a test before the student picks up a pencil tells you nothing. Let us keep moving. Question 20. Classic exam trap. A generative AI engineer at Stonebridge AI enabled inference tables on a production model serving endpoint to capture all incoming requests and outgoing responses. Several weeks after setup, the team notices that the inference table has stopped receiving new records. No configuration changes were made to the endpoint itself. Which action most likely caused logging to stop? Select one. Review the answer choices on screen. The correct answer is option D. 10 MB oversized payloads skip entries. Not all logging. Inference table logging stops when the destination table's schema is changed, when the table is renamed, or when the table is deleted. Altering the schema by adding a column breaks the logging pipeline's expected table structure and causes it to stop writing new records entirely. HTTP 404 errors are not among the documented error codes. 401, 403, 429, and 500, that may cause individual log entries to be skipped, and a cluster of errors does not fault the entire logging pipeline. The 128 concurrent request limit governs endpoint throttling behavior rather than logging. Exceeding it generates HTTP 429 responses for clients, but does not suspend inference table writes, and the limit can be increased if needed. Payloads exceeding 10 MB are skipped on an entry-by-entry basis. Only those individual oversized records are omitted while all other requests within the size limit continue to be logged normally. 3 takeaways from this session. First, storage-optimized AI search endpoints unlock 1B plus vector scale with 1020x indexing throughput at 250 millisecond latency cost. Second, inference table logging stops silently when the destination schema changes. Never alter table columns after enabling capture. Third, MLflow Champion aliases decouple inference pipelines from version numbers, enabling zero-code change model promotion. Endpoint tiers, silent logging failures, position-sensitive metrics, these are the details DGAI rewards knowing. Lock them in, and any variant of these questions becomes recognizable.